In this video, we introduce the fundamental concept of a basis, and then we give a formal definition of what dimension really means. Now, so far we've looked at the idea of linear combinations, spanning sets, and linear independence. And in some sense, a basis is a coming together of all those ideas. Right. So let me actually start with the formal definition, and then we will use an example to kind of expand our understanding of the definition, and then maybe do some other examples after that. So let S be a set of vectors. Right. So we have a set of vectors where each of the vectors is an element of our n-dimensional Euclidean space, right? We say S is a basis for that n-dimensional Euclidean space, provided these two things occur. So provided, one, S is linearly independent, right? And the span of S is equal to all of Rn. Right? So if our set S of these vectors, if this set satisfies both of these properties, we say that our set is a basis for Rn. And in a nutshell, what it means is every vector in this vector space can be written as a linear combination of these vectors in a unique way. So there's one and only one linear combination of these vectors that will produce every vector in this space we call Rn. All right, so let's take a look, and let's start with R2. All right, so if we look at R2, well, as a set, we know that, and I'll write these vectors as columns, so we know that R2 is a set of vectors with two components, and those two components can be any real number, right? Now, there is what's considered a standard basis for this. In other words, there's a standard set of vectors that can be used to generate all the vectors in R2. And some of you may have already seen those two vectors if you've studied Calc 3 or physics. Possibly you may come across these particular vectors. So I'm not going to say the name right now. I'm just going to show you kind of the algebraic way of how we can come up with these vectors. So let's take the general vector in R2. So let's start with the xy, right? Two components. Well, I can write this single vector as the sum of two vectors, where the first vector is x0 and the second vector is 0y. So essentially what I'm doing is I'm splitting the two components into two separate vectors. So I'm keeping the first component as x, and then I'm making this second component equal to 0, and then for the second vector, I'm making the first component equal to 0, and I'm keeping the second component as y. Right? So it's almost like I've decomposed this single vector into a sum of two vectors, but I'm choosing them in a very simple, easy to understand way, just keeping each component in a separate vector. But now what I can do, I can actually use my distributive property almost in reverse, and I can factor out the x. So I can put the x in front of the vector, and then this will be 1, 0, right? So essentially doing the reverse of my scalar multiplication. Instead of distributing the scalar, I'm now factoring it out. But having a 0 here, it doesn't change, right? And then do the same thing with my second vector. Factor out the y, and then I have 0, 1. But if you look at this, right, this is really just a linear combination of these two special vectors. So with this simple line of logic, what I've shown is that every vector in R2, right, and there are infinitely many of them, can be written as a linear combination of the vectors 1, 0 and 0, 1, right? And so the question is, are these two vectors linearly independent? So are the vectors 1, 0 and 0, 1 linearly independent? Well, yes, right? So note 1, 0 and 0, 1, these two vectors are linearly independent, and we have several ways that we can check to see if vectors are linearly independent. The easy way to check when you have just two vectors is to realize that they are not scalar multiples of each other, right? So these two vectors are linearly independent because they are not scalar multiples of each other. So in other words, it means that they point in different directions. So scalar multiples of each other. So what does this show? This line here shows that every vector in R2 can be written as a linear combination of these two. So this line here actually shows that R2, or let me write it like this, the span of these two vectors, the 1, 0, 0, 1, that's equal to R2, right? And then this note down here shows that, again, these two vectors are linearly independent, right? So 1, 0, 0, 1 are linearly independent, and I am being redundant here, but it's for emphasis. And what it means is that it means these two vectors, they form a basis for R2, right? So hence, so if I write this set, my 1, 0, 0, 1, right? So this set forms a basis for R2. All right. So now this is kind of the algebraic way. Now since R2 is very easy to visualize, it's just our xy plane or Cartesian plane, let's just actually look at these two vectors. Well, if I draw these vectors, both of them with the initial point at the origin, this vector 1, 0 would go from the origin, and then it would terminate 1 unit in the positive x direction, right? And then the vector 0, 1, again, if I draw it with the initial point at the origin, would terminate 1 unit in the positive y direction, right? So let me just put a little mark there. So that's 1, that's 1. And these two vectors are actually referred to as the standard basis for R2. And you might know them as the vectors I and j, right? So some of you would have seen the vector 1, 0 is the vector I, 0, 1 is the vector j. Well, in linear algebra, we tend not to use I and J, and you might also know K, and I'll talk about those in a little bit. But instead, we use a slightly more general description for these standard basis vectors. We refer to this vector here that has a 1 in the first position and then a 0 in the second position. We refer to it as E1. So E1 is the vector 1, 0. And like I said, some of you might know this as the vector I. And then similarly, we refer to E2, or we use E2 to denote the vector 0, 1. So then this would be E1, and this would be E2, right? And there's a reason why we use the e's, and when I talk about the other Euclidean spaces like R3 and R4, you'll see why this notation extends very easily, right? So we can refer to these two vectors as forming a basis for R2. More specifically, they form a standard basis, right? So E1, E2 represents the standard basis for R2. So the fact that we refer to this as the standard basis, it is almost implying that there could be other bases for R2. And yes, as long as we can find two linearly independent vectors in R2, they would form a basis for R2, right? So let's make this note. So any set of two linearly independent vectors in R2 forms a basis for R2, right? And the reason why is because as long as these vectors don't lie on the same line, or they generate the same line, what you end up getting is something like this. So in terms of them spanning the entire space, it's like you can scale the red vector by any constant. That simply generates your y-axis, if you will, right? Positive scalars would extend it upwards, negative scalars would extend it downwards. Similarly, scaling the blue vector E1, that would just generate your x-axis or your horizontal axis. And then when you combine them, doing linear combinations, what you end up getting now is your typical grid. So you get all your lines like this, right? So the horizontal lines that I've kind of shifted up, those are all the different copies of, scalar multiples of E1, right? Because they're parallel. And then similarly, if I do all the scalar multiples of E2, then I get my vertical lines. And by then, I can form any vector I want in the plane by combining these two. So for instance, any vector that looks like this can be expressed uniquely as a linear combination of E1 and E2. The whole idea of having the non-standard basis is that your grid isn't the typical rectangular grid that you're used to, like you see on your graph paper, but in fact, it would look like those skewed, those isometric graph papers, that example that we worked on previously, right? So just to give you an example of this, so suppose my vectors now, so I won't use the red and the blue, but let's say I have any vector, so a vector like this, and then any vector that doesn't form the same line, let's say a vector like this, right? then if I did the same thing, this is how I can generate my entire plane, right? Again, any scalar multiple of this vector would lie on this line. Any scalar multiple of this vector would lie on this line. And then when I do my linear combination, so add a scalar multiple of this to any scalar multiple of this, this is how I generate all my other, essentially, this is my grid, right? This is my grid. So geometrically, again, these basis vectors now, it gives you a way of generating all the vectors. But if you're using a non-standard basis, then your grid doesn't look like the typical rectangular coordinate system. It's more like a parallelogram sort of coordinate system. But again, any vector in this plane can be written as a linear combination of these two, right? So for instance, this green vector here, I could say it looks like roughly maybe negative 1.5 times this vector plus 2 times this vector, right? So think back to that exercise where we worked with that isometric grid where we had these two vectors and we had to find linear combinations of them and we could sketch them. That's the same idea of using a non-standard basis, right? So the big thing is we want to be able to determine when a set of vectors would form a basis or not. So let's take a look at this question, right? So could this set be a basis for R2, right? And let's say we did it without sketching, right? Because sketching only helps, again, when you're working with something that's 2 or 3-dimensional, right? So could this set be a basis for R2? Well, algebraically, what it means is every vector in R2 would have to be expressed as a linear combination of these two in a unique way. So there will be one and only one solution, right, to a certain linear system. So let's see if this is possible, right? So let xy be our vector in R2. And then let's see if we could say, does this equation always have a unique solution, right? So does C1 times negative 2, 4 plus C2 times 1, negative 2 equals xy, right? Does this equation always have a unique solution? This is now the question that translates into linear systems that will help us answer this particular question. Not just is it consistent, but now does it always have a unique solution for every xy, right? Well, we know how to put this in our augmented form, right? Now we can do our Gaussian elimination and see if the system is always going to be consistent regardless of my choice of x and y. Will I always have not just a consistent but a unique a system that has exactly one solution for every vector that I could put here, right? Well, if I go ahead and do my elimination, you can see, let's see what's going to happen, right? So if we take negative 1/2 times rho 1, then that gives us 1, negative 1/2, and then negative 1/2 x. Second row stays the same. Then if I take 4 times, or negative 4 times the first row, add it to the second row, that gives me 1, negative 1 half, negative 1 half, x. And then this is eliminated, but so is this, right? And then I have 4, let's see, negative 4 times 1 half, so that's 2x plus y, right? So we can see several things here. This system is not always consistent, because if 2x plus y is not equal to 0, then I won't have a solution to the system, right? And we can also see that, yeah, we're missing a pivot, right? So this system never has a unique solution, right? So this system is always it either has infinitely many, that's when this expression is equal to 0, or if this expression is not equal to 0, then the system is consistent, right? So let's actually write that down and then use that fact to answer a question about whether or not that set could be a basis. So this system is, or let's say it this way, this system is inconsistent when 2x plus y is not equal to 0 and has infinitely many solutions when 2x plus y is equal to 0, right? So we will never be able to have a unique solution for every xy, right? So this implies that our set S, let me restate it, negative 2, 4, comma, 1, negative 2, could not be a basis for R2. Right? Could not be a basis for R2. In fact, it doesn't pass both of those requirements. And again, if you look closely at the vectors that I chose, you realize that these two vectors are scalar multiples of each other. So they're not linearly independent. And this up here shows me that they do not span all of R2. The only vectors in R2 that can be generated are the ones where 2x plus y is equal to 0, right? If it's anything but 2x plus y equals 0, then the system is going to be inconsistent, right? So I'll just make that note, right? S is not linearly independent, or we could say is linearly dependent, right? So it doesn't satisfy that requirement of a basis, and the span of S is not equal to R2. So it fails on both counts. All right? Okay, so what does it look like for R3, R4, and so forth? Well, it's the same idea, and what I will do for those, in fact, what I will state now is the standard basis for Rn. So in general, using the same process there, so we know that Rn is now the set, and again I'll continue to write it as a column, but now we essentially have n components, x1, x2, dot dot dot, xn, where each of the xi's can be any real number, right? But using the same process that I showed you earlier of taking this single column, and first let's express it as a sum. So let's take x1 in the first component and then put zeros in the remaining components, and then 0 in the first, and then x2 in the second, and then 0 in the rest, and then plus dot 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 plus 0 0 dot 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 x sub n, right? So basically, for each component, we keep the non-zero entry in a single column, and all the other entries are 0. So then, when I factor out each of the xi's, like starting with x1, then I would have a 1 in the first position and then 0 elsewhere. Plus, when I factor out the x2, I'll have a 0 in the first position, a 1 in the second position, and then 0 elsewhere. And I do that for each of these columns. And then what I'm ending up with now is like these binary vectors, right? Where they're filled almost entirely with 0, but just one component is equal to 1. The very last one, that's xn, it will be 0 0 dot dot dot, say 0 and then 1, like that, right? And these now form a standard basis for Rn. And what we do is we call, so this for instance is E1, this is E2, and this is En. And basically, the subscript here tells me what entry is equal to 1. So in E1, the first component is equal to 1, and all the other components are 0. In E2, the second component is equal to 1, and all the other components are equal to 0. In En, the nth component is equal to 1, and then all other components are equal to 0. So let's write that down. So E sub I, right, is a column, or is the column with a 1 in the ith component and 0 elsewhere, right? And this set of e's, so the set E1, E2, dot dot dot, E sub n is the standard basis. So is the standard basis for Rn, right? And it's not a coincidence that this set has n vectors, right? And it's used to represent the standard basis for Rn. In fact, this is what leads us to the definition of dimension. The number of vectors in a basis for Rn is defined as the dimension of that space, right? So the number of vectors in any basis, the standard or non-standard basis, so the number of vectors in a basis for Rn is called its dimension, right? Which is why we actually say like R2, because it has a standard basis that consists of 2 vectors. R2 is 2-dimensional. So it's more a geometric thing and less, it's more an algebraic thing and less a geometric thing. And so we denote dimension by dim. And then, so for instance, if I would to say, what is the dimension of Rn, then that would be n, right? So the dimension of R2 is 2, the dimension of R3 is 3, and it's because all of those Euclidean spaces, right, can be generated using a standard basis or any basis consisting of a finite number of vectors. So just with these n vectors, I can generate all the vectors in Rn using my basic linear combination. So I can scale them by any constant I want, and then I can add the results together, right? And for this reason, we refer to Rn as a finite dimensional space, right? So Rn is described as a finite dimensional space or set of vectors, right? And again, it keeps going back to what I always try to emphasize, in that we're using a finite number of vectors and we're able to generate an infinite set of vectors, right? All right, let's do one more example of this and see. Let's look at something in R3, right? So here's another example. And this one will be similar to what we just did with R2, but now let's ask ourselves this. Could the set S, so here are my vectors 1, 1, 0 and 1, 1, 1 and 0, 1, negative 1. So could this set be a basis for R3, right? So we have 3 vectors, right? So at least we have the right number, right? We don't have too many or we don't have too few. But the question is, can every vector in R3 can be represented uniquely as a linear combination of these 3 vectors? So the way we answer it, unsurprisingly, is to go back to our linear system, right? So let me translate this into a linear system. So first, since we're now talking about an entire set of vectors where there are infinitely many of them, I'm not just going to pick one, but let's write down the general vector in R3, right? And then we're going to ask ourselves, is there always a unique solution of this equation? C1 times our first vector, and then plus C2 times our second vector, and then plus C3 times the third vector, and then I have on this side x, y, z, right? Now what we could do, right, we could certainly go ahead and use our Gaussian elimination, and we could go ahead and reduce it and see, do we have any free variables or anything like that, right? But let's take a slightly different approach. Remember, we have several ways that we can interpret this. I'm going to write this in matrix form. So matrix form is where we keep our coefficient matrix like this. And then we have the constants that we, are treating as our variables now. And then this is our b, just as our b is not a set number or I should say these aren't set constants. These are any order triples x, y, z. And we want to know, does this system, right, always have a unique solution? But this is where we can rely on what we know about the invertibility of a matrix and the determinant. So if I call this my A, I know that if the determinant of A is not 0, then the matrix is invertible, and then this matrix equation always has a unique solution. So I don't even have to use my Gaussian elimination. I can do something like determinant. So let's write that down and then actually answer the question. So if the determinant of A is not equal to 0, this implies that A inverse exists, right? And this system, right, must have a unique solution. And this system must have a unique solution. Well, how does that help us answer this question? Well, it means that no matter what I put for x, y, z, right, I will always have a way of figuring out what the scalars would be that would satisfy my linear combination up here, right? So in other words, whatever I pick for x, y, z, which would represent any vector in R3, if this coefficient matrix is invertible, then it means the columns would naturally form a basis for R3, right? Well, let's check to see the determinant. Now, the numbers are fairly, this doesn't really seem like a difficult determinant to compute. I think we've computed way more difficult determinants. Now, I could either use a first column or first row expansion. Let's just go with the first row. Let's just go with the definition. So let's take the determinant of A, and just as a reminder, that's A11 times C11 plus A12 times C12 plus A13 times C13. A11 is 1, C11 is negative 1 squared, and then let's just do our minor now. So it's negative 1 minus 1. So that's negative 1 minus 1. And then plus, I have another 1 there, and now C12 is negative 1 to the third power, and let's write down its minor. So that will be negative 1 minus 0. And then my A13, since that's 0, I know this third term is going to be 0, right? So let's see, as long as if this determinant is not 0, then we're good to go. So this is a 1, so I have negative 2 here. And then this is a negative 1 times a negative 1. So this is a positive 1. And there we go. So our determinant comes out to be negative 1. It's not equal to 0. So therefore, these three columns, let me scroll back up here, these three columns form a basis for R3. All right? So really nice solution. We can make use of, again, determinants and invertibility to answer this new question, right? So since the determinant of A is not equal to 0, so this implies its columns. So the columns of A, which are my original vectors, so the columns of A form a basis for R3. Every vector in R3 can be written uniquely as a linear combination of those columns, right? Okay, so that ends our example in this particular video. An important definition, this idea of a basis and the concept of dimension now that is more an algebraic thing than something that's geometric, which means we can extend the concept of dimension to a lot of other things, which we're going to be doing here pretty shortly. So why don't you tune into the next video and see what that's all about. See you then.